Good morning, everyone. My name is Diego Marescotti, and before I get started with the presentation, please allow me to thank the organizing committee for the invitation to join this year's forum on tobacco harm reduction. It is a pleasure to represent Philip Morris International in this scientific venue, and I look forward to joining inspiring discussion over the next 2 days. As anticipated, today's talk is entitled System Toxicology Assessment of a Representative E-Liquid Formulation by Using Human Primary Bronchial Epithelial Cells. And in the next 15 minutes, I will describe what our company has developed in the context of preclinical in vitro assessment of flavored e-liquids. As we all well know, cigarette smoking is recognized as one of the leading causes of many preventable diseases. Despite the evidences which link the use of combustible cigarette with premature mortality, the prevalence of smokers still remain high. While the best way to reduce tobacco-related health risk is to quit tobacco use altogether, it is also recognized that quitting attempts often fail and that long-term cessation rates are low. It finally became evident the importance to identify alternatives and more successful strategy aimed to increase individual and public health. It is in this context that the tobacco harm reduction strategy was expanded to include the use of the so-called reduced risk products. The concept of less harmful product was introduced for the first time in 1991, where an editorial from Lancet was suggesting that the use of less harmful nicotine-delivering products should be considered. 16 years later, the message was further reinforced by requesting more effort in developing low-risk products which would still prove to efficiently deliver nicotine like combustible cigarettes. This is also very much in line with the recognition by the FDA that it's not nicotine that makes cigarette smoke so harmful, but rather the inhalation of thousands of harmful chemicals formed during the burning process of tobacco. To further support the notion of RRPs, the Population Assessment of Tobacco and Health Study, also known as PAS study, has indicated that more than 20 million of adult smokers would be indeed interested in less harmful tobacco products, particularly if they could receive truthful and accurate information on their potential risk. The winning strategy to achieve effective tobacco harm reduction is summarized by the harm reduction equation, which describes the fundamental criteria for making a significant impact on public health by converting the greatest number of existing adult smokers to use reduced risk products. In particular, few important steps are needed to make this common sense approach a reality for millions of smokers. To ensure a consistent consumer switch, you first need to develop a range of satisfactory, less harmful alternatives to cigarettes. Second, smokers need to be accurately informed about the harm reduction potential. It is equally important to inform them that RRPs are not risk-free, and therefore quitting tobacco or nicotine altogether remains the best option for reducing the risk of smoking-related disease. Finally, these alternatives should be appealing to all those smokers. They should deliver a taste and sensory experience that leads smokers who would otherwise continue to smoke to switch. With regard to sensory experience and product acceptance, the use of flavoring agent has an important role to play. As shown by survey results obtained in the context of the Population Assessment of Tobacco and Health Study, it appears that the proportion of non-flavored products used by e-cigs users is smaller as compared to cigarette users. This further highlights the importance of flavoring agents for the acceptance of alternative products. The use of flavoring agent is mostly associated with e-cigarette. These products are devices that heat a solution, known as e-liquid, to generate an aerosol which is then inhaled by the user. All e-liquid solutions are composed of a base liquid made of propylene glycol, vegetable glycerol, and nicotine in variable proportion. Finally, a combination of different flavoring substances characterizing each unique product is added to complete the formulation. Many of these flavor additives, usually found in food, have been extensively assessed by the Flavor Extract Manufacturer Association expert panel and are generally recognized as safe when ingested. However, for the majority of the flavoring substances, their effect on the health of consumer when inhaled are unknown and will benefit from further study. The need to have better characterized products through a rigorous and more extended product assessment is further emphasized by several scientific studies which are showing contrasting evidence on their use as potential reuse products. To fill up current product assessment gaps, we recently developed and used a multi-layer framework to systematically evaluate the potential impact of the e-liquid and their corresponding aerosol, using human in vitro models and system toxicology approach. This assessment paradigm is intended to be an important complement to the required regulatory safety toxicological data and is in line with the TOX 21 framework, which advocated the use of high throughput method to generate mechanistic data. The toxicological assessment presented here is a case study performed in the context of the flavor toolbox extension introduced in our previous publication. This assessment relies on a well-established three-pillar approach, which was also recently employed to investigate the effect of different base e-liquids, where it proved useful in demonstrating increased toxicity upon nicotine addiction to the PG-VG mixture and cytotoxic effect proportional to the PG content of the mixture. In this study, a real-time cellular analysis, so-called RTCA, was performed to evaluate cellular cytotoxicity. A panel of imaging-based high-content screening endpoint was used to analyze cellular phenotypic changes, and a combination of gene expression analysis and computational model was used to gain a deeper understanding of changes occurring at molecular level. The target of the presented assessment is a representative worst-case scenario mixture designed with a novel combinatorial flavor group based, which I'm going to explain in details in the next slide. The classical approach to evaluate the safety of a flavoring substance for inhalation would normally require a series of in vivo studies on individual substances. But given the large number of flavoring substances that can potentially be used in cigarettes, such approach would not be time and cost effective and would require too many experimental animals. Therefore, we use a novel combinational flavor group-based approach using standard and system toxicological method to acquire information on the safety of flavoring substances by inhalation. Under this approach, a list of flavoring substances that can potentially be used has been defined and subsequently clustered to predefined chemical groups of structurally related substances that are expected to exhibit similar metabolic and biological effects according to the European Commission regulation. Using a combination of predictive software and extensive literature review, toxicological data for the flavoring substances in the list were collected. Following this, at least one flavoring substance predicted to possess the worst toxicological profile was selected from each chemical group as the flavor group representative of FGR. The flavor concentration of each FGR was chosen to be similar or higher than the concentration used in the commercial formulation. Finally, a mixture of the FGR was generated for testing both in vitro and in vivo model. Current presentation is, however, only focusing on results generated with in vitro system based on the use of primary normal human bronchial epithelial cells, also known as NHB. And I'm now going to show you the finding obtained in each step. As previously anticipated, in the first step, we use impedance-based RTCA to assess the toxic effect of the 28 flavor mixture compared with that of the corresponding base solution. A range of different concentration was assessed for both conditions, and those response curves were generated to evaluate the effect of the added flavoring substances. As shown in the figure, a decrease in AC50 compared with the base solution was found for the 28 flavor mixture. To better express the flavor cytotoxic effect, we developed the so-called tox score, which is the ratio between the AC50 of the base liquid and the AC50 of any flavor solution. For the flavored mixture, a tox score of 9.84 was obtained. To understand the contribution of individual flavoring substances to the toxic effect of the mixture, each flavoring substance was assessed individually at the same concentration used in the mixture. All tox scores are reported together in the top right figures. Citronellol and alpha-pinene show the highest tox score values and were identified as potential main contributors to the toxic effect observed with the 28 flavor mixture. The remaining flavoring substances had tox score lower than 1.6. To investigate whether citronellol and alpha-pinene did indeed contribute the observed toxicity of the 28 flavor mixture, 3 new flavor mixtures were generated and assessed in NHBE cells using, again, RTCA. A flavor mixture without both alpha-pinene and citronellol, a flavor mixture without alpha-pinene, and finally a flavor mixture without citronellol. As shown here, when citronellol was removed from the mixture, either alone or with alpha-pinene, the toxic effect of the mixture decreased by more than 60%. Surprisingly, when only alpha-pinene was removed from the flavor mixture, the tox score remained high. Additionally, the tox score of the citronellol-free mixture with or without alpha-pinene did not differ. Together, this evidence suggests that although cytotoxic when tested individually, the addition of alpha-pinene to the flavor mixture did not influence the cytotoxicity of the tested mixture. In fact, the tox score did not decrease when the flavoring substances was removed. Finally, the flavor mixture lacking both alpha-pinene and citronellol induced a higher tox score than the mixture containing the individual flavoring substances. This finding illustrates the potential interaction effect that can occur when mixing flavoring substances. Together, these results suggest that citronellol is one of the main contributors to the toxicity of the mixture. Alpha-pinene did not contribute to toxicity when used in the context of the tested mixture. And finally, the interaction between flavoring substances within a mixture may also impact the final cytotoxicity of the flavor mixture itself, making the assessment of mixture even more challenging. In the second step of the assessment, we selected the 28 flavor mixture, the two flavor ingredients with the highest tox score, alpha-pinene and citronellol, four other flavor ingredients with lower tox score, with only eugenyl acetate and eucalyptol shown here, and the three flavor mixture in which alpha-pinene and citronellol were omitted individually or simultaneously. Cells were assessed at various time points, with only 4 hours shown here. Phenotypic changes using a battery of toxicity-related high-content screening endpoints, such as mitochondrial health and oxidative stress, were used to further characterize the flavor-specific effect compared with those of the base solution. The results of this comparison are shown in the figure, where circular bar plots are used to represent the minimal effective concentration ratios among base solution and flavor mix for each high-content screening endpoint. As it can be observed in the top left figure, most of the investigated endpoints show the greater effect of the 28 flavor mixture than that of the corresponding base E liquid. Upon removal of selected flavors from mixture, we observe a decreased effect of the mixture. Finally, use of this technology also allowed us to gain additional insight with regard to the effect of each individual flavor. The last step of the flavoring substances assessment workflow is based on a system toxicology-based approach that uses transcriptomic data and causal biological networks that are describing biological processes or mechanisms occurring in respiratory cells, such as cell proliferation, cell stress, inflammatory process, and cell fate. These computable network models are used to translate differentially expressed genes into network perturbation amplitude for each of the biological networks. This methodology can thus quantify and provide a more detailed understanding of molecular changes triggered by the exposure. The bar graph is representing the relative biological impact factor, or so-called BIF score, which is a holistic score that describes a system-wide effect of all biological processes perturbed after an exposure. So in this example, after 4 and 24-hour exposure, and for 2 dilution of the 28 flavor mixture and the base solution. The highest BIF score was obtained when cells were exposed to the 0.5% dilution of the 28 flavor mixture for 24 hours. Lower effects were observed for the lower concentration or for the shorter exposure condition. This methodology also allowed to compare different conditions and to investigate whether the molecular perturbations observed are similar or not. This is indicated by the delta value, which for all flavor mixture conditions were positive and bigger than 0.76. This suggests that the network perturbations were globally similar across all flavor mixture conditions assessed. The exposure to the base solution had very limited impact on the cells, as indicated by the moderate fold change compared with the untreated cell culture. To gain a deeper insight into the exposure effect, RB value can be decomposed into their mechanistic component. The circle underneath the histogram shows the major biological processes or networks that contributed most to the BIF score at each time point for both the flavor mixture and base solution. Each network can be further decomposed into several subnetworks describing more specific biological processes. This heat map provides a detailed network perturbation amplitude, or MPA score, which clearly shows which and how the different subnetworks are impacted. Given the finding and the observation made in this case study, we can conclude that it is valuable to screen single flavoring substances and rank them on the basis of their toxicity so that manufacturers can develop and/or produce e-liquid with known toxic flavor composition and doses. It is not sufficient to assess individual flavoring substances, and this makes evaluation of the flavor mixture highly beneficial to the assessment. It is therefore imperative to complement the cytotoxic-based approach with additional tests to understand what functional changes flavoring substances exposure can trigger in cells. Before finishing with my talk, please allow me to inform you that the work described today is part of a manuscript that was published earlier this year, and that you can also find additional details on Interval, which is an online platform established by Philip Morris International to serve data transparency and reproducibility in science, enabling independent data analysis and collaboration. As a closing remark, let me thank all the contributors who made this study possible, in particular Carol Matisse, who is along with me the first co-author of the manuscript. And finally, also many thanks to all of you for your attention.